now let's talk about the Smith predictor. We didn't really design a controller for the Putney approximation, but it's kind of straightforward at this point. So, therefore I briefly mentioned the stability analysis, but if you're trying to design a certain controller, we've already covered that a lot in the semester. So, we want to achieve a 10% overshoot, and that's basically it in this case. Now, what is the Smith predictor? How do we use it? Let's start with that. We will have a certain controller. We will have our feedback structure that we always use. But then there is this system, the model. I'm going to call this model. But it will have basically a J0S and some delay in it. So I know what the mathematical model is. This is the minimum phase part, and then we will have also a certain delay part. But the Smith predictor is basically a special structure that allows us to design a controller just for G0, not the whole delay system. We will treat the system as if there is no delay at all. So designing a controller for 10 by S plus 10 is way simpler and better as opposed to designing a controller for the system with delay. But the structure here will use the system model in order to give us this opportunity. And for that, we will have a branch that matches the system's mathematical model. Let's have that basically. So we have a plus here on this branch, but here we have a minus. And the reason for this is that this part tries to match the controller and match the system with this transfer function. In order to work with this signal here, if we have a certain scope to this, if you connect the scope to this, should give us 0 output. So basically, it should generate no difference at all in order to have a working Smith predictor. So this should predict the model, match the model as it is. Now, if you remember the model matching controller, what we were doing there was to have the inverse of the system and then a certain loop transfer function as the controller. So we were using this here, which would roughly translate into this GS, but actually it would be the G inverse LS times GS. And you can see that these portions cancel each other out, and we are left with LS, basically. So this was the aim of the model mentioned controller. And here, instead of having this multiplicative cancellation, we have this additive cancellation, basically. It's the same mentality. We're canceling out the model. But, of course, not exactly, because we'll add the minimum phase part to the system back. So this is here. So let's have a minus sign here, a plus sign here, and a plus sign here. So you have to be careful because I want to match these two. They should cancel each other out. So this is plus, this comes as a minus, and I want to add this third branch here so that ideally I don't really have this part here. Ideally, this part should not exist at all. So basically, it reads to F times G0 and then the whole feedback structure. Ideally, I want to have that. And here I'm canceling it multiplicative. Here, the cancellation is additive. So that's important. Once you achieve that, once the model is correct, if the poles and zeros match exactly, if you have the correct delay model, Then you're left with fs times g0 divided by 1 plus fs times g0 here. So your closed loop transfer function becomes fs times 10 s plus 10 1 plus fs times 10 s plus 10. Actually not quite, because we will still have a certain delay part, but we will basically design this closed loop. And our actual closed loop system will have e to the power up minus s in this case. And you can see that by using the relations here. If you look for the closed loop transfer function, you'll see that in the closed loop you still will end up in a forward term that has the delay. Of course, you cannot get rid of the system delay, because it doesn't really matter what your controller is or what your control structure is. The system responds with a certain delay. Even if you're using a prediction or the Smith predictor, you will still have delay, but what we're trying to do is we're trying to get a characteristic polynomial out of this. That's the important part. We will have a polynomial. The delay will not be present in the denominator of the closed loop, but it will be in the numerator. So that's the actual difference. And the whole closed loop looks like this. Of course, you have to work it out yourself, but fs times the model s divided by 1 plus fs g0 s minus, or g0 e to the power of minus tau s plus g0, actually g model. The model s plus g0 s minus g0 e to the power of tau s. So this is basically the actual closed loop if you work it out from here. And if the cancellation occurs, ideally you will get g0 e to the power of tau s. Therefore, this part and this part will cancel each other out. You will get the characteristic polynomial will be equal to 1 plus fs g0 s, which is a polynomial which we can use to design our controller, which is nice because this was not a case if you don't have the Smith predictor. But if this is a characteristic polynomial, and if your model matches this, you will still have Ts equals f times fs times g0 s e to the power of minus tau s divided by the characteristic polynomial. You will still have that. I want to design a controller that kind of has fs g0 s 1 plus fs g0 s, but I will still have this delay part. I cannot get rid of it because it's in the feed-forward path. This is in the feed-forward path. So even if there's a cancellation here, the overall closed loop will have still this e to the power of minus tau x, but I'm still okay with that. It's not really that big of a deal. So if you, for example, design a PI controller that achieves this ocean value, the closed loop that I'm going to write down will look like this. My closed loop should be 10k s plus z divided by s squared plus 10s plus 10k s plus z, but then I will have e to the power of minus x. So I'm going to decide on the controller based on this characteristic polynomial. You can use the algebraic method, you can use the root locus method, you can use whatever you want to design your controller. But I will always know that if I use the structure, I will have this 1 second of delay in the closed loop, and that's basically it. So if I'm choosing a historical setting time, for example, if I want to have it equal to 3 seconds, I should maybe use 2 seconds of setting time for this system. Since I have only already 1 second of delay, I might match this 3 seconds mark. But then you go ahead and design your controller as you wish for the minimum phase part of the system. And if this is working, then you will get the job done. Now you can look up the details from the PDF, which I'm going to upload. Therefore, it's not really about the numerical part on how to design it, because you have the second order system, you'll have the zeta value that you want to have. And you can also see that this part here is 2 times zeta times omega n. We know what zeta is, you can work out what omega n should be, because there will be only that solution. Then you can work out what k is, z is, etc., etc. Of course, you need a certain dominant factor, and so on. But you can get rid of this delay here by using the structure, ideally, if it's matching it. And for our exam, for example, there will be no case that it's not really matching, because you will have a mathematical definition. This is the actual system here, and your model will be the same, so it should be okay. But if you're in the lab, and if you have a working system and you kind of have a mathematical model here, then you might be in trouble with the Smith predictor, because you have to be precise with your mathematical model. Otherwise, this will not work that well. Yeah, this is question 7, therefore.